Hello everyone, in this video we'll be learning about the Doppler effect for the electromagnetic waves propagating in the vacuum. First of all, we'll see the key differences between the acoustic Doppler effect and the Doppler effect for the EM waves. Then we'll see their practical applications. After that, we'll take up numerous great solved questions, and then you'll be getting a checkpoint for your own conceptual practice and you'll get its answers also. Okay, so let's begin. The propagation of the sound waves requires the medium, while as the electromagnetic waves can propagate without any medium. And the second important thing, the speed of sound may be different for the different observers, while as the speed of electromagnetic waves in vacuum is same for all the observers. Based on these two key differences, the formulas for the acoustic Doppler effect and the formulas for the Doppler effect for the EM waves will be totally different from each other. Got the idea? The formulas of the Doppler effect for the EM waves are usually derived using the Einstein's theory of the general relativity. We won't go into the details. We'll just use the necessary formulas. Got it? Note down these two key differences, then we'll go into the further details. Let's see the practical applications of the Doppler effect. The acoustic Doppler effect is used in measuring the blood flow or to detect the fetal heartbeat, while as the Doppler effect for EM waves has variety of the applications. It can be used to detect the black holes. It can be used to prove that universe is expanding. It is used to determine the spin rate of the galaxies or the stars, etc. Using this Doppler effect, the police issues the speeding ticket for the vehicles, and in order to study the weather systems, we use the next generation radars, and there we also use this Doppler effect. We'll go through all these examples in the details with the help of good questions. Once you note them down, then we'll proceed further. In this video, we'll be going through two different kind of shifts caused by the Doppler effect for the light propagating in vacuum. Number one is the blue shift and number two is the red shift. Blue shift occurs when the distance between the source and the observer is decreasing and the measured frequency is greater than the actual frequency of the waves emitted by the source. Got it? In this scenario, the measured wavelength is less, so the entire color spectrum shifts towards the blue end. That's why we call it blue shift. And in the second case, when the separation between the source and observer is increasing, the measured frequency will be less, the measured wavelength will be more, so the entire color spectrum will get shifted towards the red end, that we call as the red shift. Actually, if we take the spectrum of the light coming from the distant galaxies, that spectrum appears to be red shifted. It indicates that all other galaxies are rushing apart with respect to us, and it is true for any other observer in any other galaxy also. For example, some of your friend lives in some other galaxy and he scans the entire space and he gets the spectrum for the light coming from the other galaxies. He will also say that all the spectrums are red shifted, means from him also the galaxies are rushing apart. So from any point in the universe, if we observe, we'll find that all the galaxies are rushing apart from each other, means the universe is expanding. You can sense this expansion like as the expansion of a braid loaf. The beads on the braid loaf, you can see here, the distance between them is increasing with respect to time, like as all the galaxies in the universe, they are rushing apart. Got the idea? This was proved by the Edwin Hubble using the Doppler red shift. I hope you understood the importance. So keep in mind, whenever the separation between source and observer will be decreasing, you'll be getting a blue shift, and whenever separation between them is increasing, you'll be getting a red shift. These are two important terms. Once you note it down, we'll go into the details, we'll go into the formulas. Okay. Here I am taking up the case 1, the blue shift, means the separation between the source and observer is decreasing. It can happen in 3 ways. The source approaches the observer approaches the source, or both approach each other. So let's see the formulas. The F is given as F naught root of C plus V relative divided by C minus V relative. Whenever the source and observer will be approaching each other, the observed frequency will be higher than the actual frequency of the source. Got it? Here you can see the data. In numerator we have the positive sign, in denominator we have the negative sign. So actually the F will be greater than F naught. What is F here? F is the frequency measured by the observer. What is F naught here? We call it proper frequency, which means the frequency measured in the rest frame of the source. What is C here? The speed of light in vacuum. What is V relative here? The relative speed of the source and observer along the straight line joining them. Pay attention. It is the relative speed, and it should always be calculated along the straight line joining the source and observer. Now, in the case of the blue shift, the measured wavelength will be actually less. So the data here should be C minus V relative divided by C plus V relative. In the numerator there is a negative sign, so the lambda naught will be actually greater and the lambda will be actually less. What is lambda here? The wavelength measured by the observer. What is lambda naught? Proper wavelength. Proper wavelength means the wavelength of the electromagnetic waves in the rest frame of the source. C is the speed of light in vacuum, and V relative is the relative speed of the source and observer along the straight line joining them. Got it? So these are two important formulas for the blue shift. Okay. Now there are the cases in which the V relative is much small as compared to the speed of light in vacuum. Then we can rewrite these expression. F will be almost equal to F naught 1 plus V relative divided by C, and the lambda will be almost equal to lambda naught 1 minus V relative divided by C. I'll be proving all these expressions. You just pay attention here. Let us rewrite this formula, this one. So here I am taking the C outside of the numerator as well as of the denominator. So the expression will look like this. Do you agree? This is getting cancelled out. So we can simplify this expression. It will be F naught 1 plus V relative by C to power 1 by 2 and 1 minus V relative by C power minus 1 by 2. I hope you agree with this. This entire bracket has been shifted to the numerator, so power becomes minus 1 by 2. Do you remember the binomial approximation? It tells that 1 plus x to power n is almost equal to 1 plus nx if x is much less than 1. So in these brackets we'll be using the binomial approximation. You can treat this as 1 plus x to power n. Got it? If V relative is much small as compared to C, we can use the binomial approximation. So I am rewriting the terms. Pay attention. F will be equal to F naught, and then using the binomial approximation here, I should write 1 plus n. N is 1 by 2 and the x is v relative by c. Do you agree? Let's do the same thing here. 1 plus n is minus 1 by 2 and x is minus v relative by c. Let us simplify it further. F is almost equal to f naught 1 plus 1 by 2 v relative by c, and this is also 1 plus 1 by 2 v relative by c. So here I should write whole square. I can again use the binomial approximation in this. So the final formula will look like as f naught 1 plus 2 into 1 by 2 v relative by c. Do you agree with this? We have the final expression with us. You can check it that 2 and 2 will get cancelled out and we are left with this expression. Got it? In same manner, we can do the computation for the lambda. I am not going into that. I am leaving that for you. So I am writing the final expression here, f naught 1 plus v relative by c. Keep in mind that expression is valid if and only if v relative is much small as compared to the speed of light. Okay. Another important derivation. If this condition is satisfied, I can simplify the things here again. F is equal to, almost equal to, f naught plus f naught v relative by c. Do you agree? Shifting this f naught here, f minus f naught is almost equal to f naught v relative divided by c. So here I can write f minus f naught by f naught is equal to, almost equal to v relative by c. Okay. While doing the numerical calculation, you can take the equal to sign also. You'll get the approximated answer. This is another formula which we should learn. I can write that formula here in this format. Delta f divided by f naught is almost equal to v relative by c. Do you agree with this? Can we obtain similar formula for the lambda? Think about it. If you do the computation, delta lambda by lambda will be almost equal to minus of v relative by c. I am proving it. Lambda naught 1 minus v relative by c. Do you agree? Expand it. This lambda naught, I am shifting to the LHS. So lambda minus lambda naught almost equal to minus lambda naught v relative by c. Dividing this lambda naught here, lambda minus lambda naught by lambda naught is minus v relative by c. Another important formula. Okay, one thing we should keep in mind, these black formulas are valid if and only if v relative is much small as compared to c. Okay. You should note down these expressions because we'll be utilizing all these expressions in the numerical calculations. So once you note it down, I'll prove the similar formulas for the red shift also. Or shall I leave it to you? What do you say? Actually, the kind of derivation will be same, but I'll do it for you. Note it down. Now we'll see the details of the red shift. Red shift means the observed frequency will be lower, the observed wavelength will be higher, and the color spectrum will be shifted toward the red side. Okay, when it will happen? Whenever the separation between the source and observer is increasing, and it can happen in three ways. Either the source moves away, or the observer moves away, or both move apart. Okay. Writing the formulas for the red shift, f is equal to, I think now you can guess yourself. This time we need the less frequency in the LHS. So what I should put here in the numerator? C minus V relative divided by C plus V relative. Simple common sense. If here is a minus, then this data will be less. If here is a plus, this data will be again less. Okay. And lambda will be equal to lambda naught root of C plus V relative divided by C minus V relative. Two important formulas for the redshift. And there are the questions in which V relative is much small as compared to C. Then the F will be equal to F naught 1 minus V relative by C. And the lambda will be almost equal to lambda naught 1 plus V relative by C. And if we simplify the things here, F minus F naught by F naught will be equal to, almost equal to actually, minus V relative by C. This in turn can be written as delta F by F naught. And here lambda minus lambda naught by lambda naught is almost equal to V relative by C, which in turn can be written as delta lambda by lambda naught. Okay. If you wish, I can prove out the things again here. I am taking C outside in the numerator and C outside in the denominator. C and C, when you take common, they'll get cancelled out. So the F will be written as F naught 1 minus V relative by C power 1 by 2, and it will be written as 1 plus V relative by C power minus 1 by 2. Do you agree with this expression? Now you know what to do. We'll be using the binomial approximation. If x is much less than 1, then 1 plus x2 power n is almost equal to 1 plus nx. Okay, we call this thing as the binomial approximation. So in few question we'll get the condition that V relative is much small as compared to C. Then we can use the binomial approximation here. Pay attention. F will be written as F naught bracket 1 plus 1 by 2 and then minus V relative by C. I am explaining this part again. This is 1 plus x2 power n. So 1 plus nx. Simplifying the things here, 1 plus minus 1 by 2 V relative by C. Do you agree? Can we rewrite this entire expression? F is equal to F naught 1 minus 1 by 2 V relative by C whole square. These two terms are identical. Now again we can use the binomial. So this will be equal to F naught bracket 1 plus 2 bracket minus 1 by 2 V relative by C. Got it? So it is almost equal to F naught 1 minus V relative by C. Here is almost equal to, although in numerical calculation you can consider equal to sign, your answer will be approximately correct. Got it? Oh, I think I have derived this expression. Done. In the same way we can proceed for lambda, that I am leaving to you. Then going further for the simplification, this F was equal to F naught minus F naught V relative by C. This F naught can be shifted here. So F minus F naught, and then we can write the simple expression F naught V relative by C. Shifting the F naught here. So F minus F naught by F naught is equal to minus of V relative by C. Another important expression. Okay. Actually here is almost equal to. I repeat, in numerical questions you can take equal to, your answer will be approximately correct. Now we can go for this expression also. Here the lambda is almost equal to lambda naught 1 plus V relative by C, which in turn can be written as lambda naught plus lambda naught V relative by C. This lambda naught I am shifting into LHS, so lambda minus lambda naught is almost equal to lambda naught V relative by C. Dividing that lambda naught here, okay, so this is almost equal to V relative by C. Another important expression. In exam, there should not be any confusion in the formulas. It's simple, it's logical thing, such as in this case, what is happening? The source and the observer are moving apart, so the observed frequency will be less. To keep the observed frequency less, the measured frequency less, we should keep here negative sign and here positive sign. Do you agree? If frequency is less, then the lambda will be more. You might remember this expression, C is equal to F lambda. Okay, when frequency is less, the lambda will be more. To keep the lambda measured greater, here should be positive sign and here should be negative sign. Okay, in numerator, if there is positive sign, this data comes to be greater than lambda naught. In denominator, if there is negative sign, again this data comes greater than the lambda naught. I hope you understand the simple trick. So you can note it down. You can figure out the difference between the previous case and this case is of this sign. The sign got flipped. In previous case here was positive, okay, in previous case here was negative, and same analogy you can do for the remaining formulas. I urge you to learn this left hand side of the formulas. You can skip that calculation. While doing the question, if you find that the relative speed along the straight line joining the source and observer is much small as compared to C. For example, in some question you find a car is moving with the speed of 28 meter per second, and then use the Doppler effect formula. 28 meter per second, 30 meter per second, 500 meter per second are much small as compared to 3 into 10 to power 8 meter per second. Then you can use these formulas. Although these are approximations, but your answer will be good up to a great degree of accuracy. Note them down, then we'll go further. We'll take up numerous beautiful questions based on these formulas. First question, and a simple one. A star is receding away from us, so the light will be red shifted. We have to find the speed of star. Got it? Simple formula based question. You may give it a try, and then I'll be simplifying the things on board. I hope you are done with your calculation and got the correct answer, which is about 685.66 kilometer per second. Computation is pretty simple. This light is red shifted, star is receding away from us. Got it? So the observed wavelength will be more and the observed frequency will be less. It means we can write delta lambda by lambda is almost equal to V relative by C. Got it? Actually, delta lambda means what? Delta lambda means lambda minus lambda naught. Star is receding away, so the measured wavelength will be more as compared to the proper wavelength of the source. Means this parameter is positive, this parameter is positive, V relative is the relative speed, which is positive, C is positive. So this formula will work very well in this case. Delta lambda is given as 15 angstrom, lambda was 6563 angstrom. Okay, V relative is unknown, C is 3 into 10 to power 8 meter per second. When you do the computation, the V relative will be almost equal to 685.66 kilometer per second. Note it down, then I'll bring up the next question and ask if you have any doubt. It's another simple formula based question, so if you wish, you may give it a shot, then we'll discuss the answer on the board. I hope you got the correct answer, which is a very tiny number. I'll prove it. Since your car is approaching towards the radio station, so the observed frequency will be more. The delta F is equal to F minus F naught, okay, and F is here greater than the F naught. The observed frequency is greater than the actual frequency of the source. So we can write the formula. Delta F is almost equal to F naught V relative by C. How much is F naught? F naught is 91.5 megahertz. How much is relative speed? The radio station is at rest with respect to the driver of the car, and the car is moving with the speed of 20 meter per second. So the relative speed will be 20 meter per second only. Putting that data here, and the speed of light in vacuum we take as 3 into 10 to power 8 meter per second. Got it? Simple computation. You can solve this number. After doing the calculation, you'll get it. See, when you drive your car, then actually there is a Doppler shift in the EM waves, but that shifted frequency you cannot sense, because the shift in frequency is pretty small. So in daily life, when we are in motion, we do not observe the Doppler effect in the electromagnetic waves. Can you tell me the reason? Actually, the relative speed is much small as compared to C. Got it? Note it down, then I'll bring the next brilliant question. It's pretty interesting question. Read the language of the question. I hope you'll enjoy it. If you are driving a car and you wish to get every traffic signal as green, at what speed you should drive? This question will give you the idea. Think about it. For your car, there is no red signal. Every light is green. It will be amazing. But to get that amazing thing, what speed do you require? You can calculate it. Then I'll be simplifying the things on board. Enjoy it. I hope you got the correct answer, which is 0.26 times of the speed of light in vacuum. I am doing the calculation here. Pay attention. Here the light appear green to the driver. Got it? So the lambda green is equal to lambda red times root of C minus V relative divided by C plus V relative. You understand how we are able to write this formula? Lambda green is given as 500 nanometer. Check the language of the question. Lambda red is given as 650 nanometer. Okay, and then C we already know, 3 into 10 to power 8 meter per second will get the relative speed, C plus V relative. Why I have used this formula? The logic is simple. This time the observed wavelength is less as compared to the original wavelength of the electromagnetic wave. So if observed wavelength is less, the wavelength measured by the driver is less, it means in the numerator what sign I should choose? Logical explanation. In numerator I should be choosing a negative sign. Then the observed wavelength will become less than the proper wavelength, actual wavelength of the EM wave. Okay. Here in the denominator, again I should choose a positive sign, then only the measured wavelength by the driver will be less as compared to the wavelength emitted by the source. the proper wavelength. Okay. Rest all is simple mathematics. You can cancel out this unit nanometer and you can do the calculation by squaring both sides. So I am doing it here. 50 by 65 whole square is equal to C minus V relative divided by C plus V relative. Simplifying it further, the V relative comes out to be 0.26 C. So if the driver drives the car at this speed, all the red signals will appear green to him. Any normal human being can attain this speed or not? You know the answer. Normal people can never attain this speed. And although suppose some driver attains this speed, then he might feel that all the signals are green for him. But again, the police inspector can issue him a ticket for overspeeding. Okay. So it is an interesting question. In your life, if you want an uninterrupted ride through the traffic crossings or the intersections, you should be driving at such high speeds. Keep enjoying. I'll bring up the next question then. Again, a brilliant question. So I urge you to give it your best shot. Then we'll discuss the answer on the board. I hope you are done with your calculations. So I'm simplifying the things here. Suppose this is the Earth. Okay. And here are the 3 points of our interest. The center of that galaxy, point A and point B. The center of galaxy is moving away from us with the speed UG. With respect to the center of galaxy, the point A has the speed Vt in this direction and the point B has the speed Vt in this direction. Got it? We want to determine the relative speed with respect to the Earth. Our observer is situated on the Earth. So first of all, we obtain the velocity of A with respect to some observer on the Earth. Here you consider some observer, name it as E. Okay, observer on the Earth. So once we get that velocity, using the magnitude of the velocity, we can obtain the relative speed. Velocity of A with respect to E, how we can obtain? Actually, we can write this as velocity of A with respect to the C, the center of the galaxy, plus the velocity of the center of galaxy with respect to the Earth. Okay, this concept is taught in the chapter relative motion. Now similarly, we can write for B. Velocity of B with respect to the Earth is actually equal to velocity of B with respect to the center of galaxy plus velocity of the center of galaxy with respect to the Earth. Do you agree? Here we are using the vector sign, so I'll designate the positive and negative direction because in vector we need to take care of the directions. Velocity of A with respect to E, I am going to put up the data. VA with respect to C, in this direction we choose the negative sign. So minus 0.4 into 10 to power 6 plus velocity of center with respect to the Earth means 1.6 into 10 to power 6 meter per second. Do you agree? Okay, so it comes out to be 1.2 into 10 to power 6 meter per second. Similar computation we do for VBE. It is in positive sense. So the data of Vt is known to us. It was 0.4 into 10 to power 6 meter per second. So the velocity of B with respect to C, I am going to put as 0.4 into 10 to power 6 plus velocity of C with respect to the Earth was given as 1.6 into 10 to power 6 meter per second. Do you get this? Simplifying it, we get 2 into 10 to power 6 meter per second. Now if I ask you that point A or point C or point B, they are coming close to the earth or they are moving away, the galaxy is rotating as well as receding, the correct answer is all the points are going away from us. The universe is expanding. Or even you can verify this. This velocity has positive sign, this velocity has positive sign, this velocity has positive sign. It means with respect to the earth, all are going away. Positive sign. Got it? If all the points are going away, it means whatever light, whatever electromagnetic waves will receive from these points, that will be blue shifted or red shifted. The source of light is going away. If source of light is going away, the observed frequency will be less. It will be red shifted. You got it? Now for red shifting, we can use the formula. So that computation I am doing here. Suppose f dash a is equal to f naught and observed frequency will be less. So 1 minus this data for a is here 1.2 into 10 to power 6 divided by 3 into 10 to power 8. Got it? In hertz you'll get the answer. What is f naught given to us? F naught is 6.2 into 10 to power 14 hertz. So you can do the computation. You will get your answer as 6.175 into 10 to power 14 hertz. Okay, this data if you write in detail, it is actually 6.200 into 10 to power 14 hertz. So after decimal we have the availability of data up to 3 digits. So your answer should also carry the data after decimal up to 3 digits. Got it? Now going for f dash b. This observer will receive some frequency, will measure some frequency for the EM waves sent from point B, that I am writing as f dash b. It will be equal to f naught 1 minus this data is 2 into 10 to power 6 divided by 3 into 10 to power 8 hertz. It comes out to be 6.159 into 10 to power 14 hertz. Keep in mind these all points are going away with respect to the earth. So from any point of this galaxy, if we get the light, it will be red shifted. And figuring out the differences of the frequency, the astronomers can actually determine the spinning speed of this galaxy. Got it? Note it down, then I'll bring up the next important question. Another beautiful question is on your screen, so I urge you to pause here and give it your best shot. Then we'll be discussing the answers. I hope you are done with the calculations. So the answers are, it won't get any speeding ticket as the speed of the speeder is 31 meter per second. And the answer to the second part is 7600 hertz. I'm starting the solution here. Pay attention. Here is the police car, which is moving with the speed of 38 meter per second. It emits the electromagnetic waves of frequency f naught. F naught is given as 3 into 10 to power 10 hertz. Okay. Here is the speeder. Let's say it is moving with speed Vs. This is taken with respect to the ground. Okay. And we need to determine the speed Vs. That is our first target. So I'm starting the calculations. Suppose these waves reach here to the metal body of the speeder. Okay, here the observed frequency I'm writing as f1. So the vehicles are approaching, the police car is approaching the speeder. It means the f1 will be more or less, f1 will be more than f0. So f1 should be written as f0 1 plus v relative by c. Do you agree? This time I'm using the equal to sign. And why we have used this formula? Obviously the speed of the speeder or the speed of the police car are much less than the speed of light. Since v relative is much less than the speed of the light in vacuum, we can use these formulas. Got it? Okay, now comes the second scenario. Electrons in the metal body will absorb these electromagnetic waves and will vibrate at the same frequency. Whatever frequency they observe, they receive, with the same frequency they will vibrate, and then they will emit the electromagnetic waves of the same frequency. It means for the second diagram, this speeder becomes the source, okay, and it emits the electromagnetic waves of the frequency f1. Because the electron here received the frequency f1, they absorbed it, they started vibrating with the same frequency f1, and they'll emit the electromagnetic waves of the same frequency f1. Now the police car is the observer, okay, which is moving at a rate of 38 meter per second. Suppose the police car observes the frequency which I write as f1 dash. So f1 dash will be more or less, obviously the police car is approaching the speeder, it means the f1 dash should be more. F1 dash will be equal to f1 1 plus v relative by c. Do you agree? Value of f1 is already available. I am submitting that value. f0 1 plus v relative by c, that is the value of f1, and here is another 1 plus v relative by c. So the f1 dash comes out to be f0 1 plus v relative by c whole square, and we can use the binomial approximation because v relative is much small as compared to c. So this will be f0 1 plus twice of v relative by c. Actually here should be approximately equal sign, but I told you numerical question we can take the equal to sign and we'll get the approximated answer. We need not bother about the thing. Now from here I am doing some computation. This f1 dash minus f0, okay, I am simplifying the things here, can be written as 2 times f0 v relative by c. The difference of these two frequencies is known as the beat frequency, okay. I can call this as f beat. Now it is an important expression. In next question also we'll be utilizing this expression, so I urge you to learn it, to remember it. Now we have the availability of all the data, so we can do the calculation very easily. According to the data given in the question, f beat is 1400 hertz, okay, is equal to 2 times f0. The f0 was 3 into 10 to power 10 hertz. V relative is unknown, divided by the speed of light in vacuum is 3 into 10 to power 8 meter per second. V relative is equal to 7 meter per second. This is an important data. If the relative speed is 7 meter per second, it means this Vs should be actually equal to 31 meter per second. Do you agree? Check it, 38 meter per second and 31 meter per second. The relative speed will come out to be 7 meter per second. Since its speed is less than the speed limit, so it won't get any speeding ticket. I hope you understood this calculation. It was simple one. Now here is the space, so I can find the second answer also. This all was the calculation for the first part. Pay attention. For second part, question is asking us the F beat. If the electromagnetic waves are reflected by the stationary object, this police car is radiating the electromagnetic waves, they'll get reflected by the stationary object also. So I am calculating that beat frequency. It will be 2 times F naught. F naught is 3 into 10 to power 10. V relative, stationary objects are at rest, so relative to them the police car is moving with the speed of 38 meter per second and the speed of light is 3 into 10 to power 8 meter per second. Got it? Your answer will come in the hertz. Doing this computation will get the answer as 7600 hertz. Okay, so from the stationary object the reflected waves will give us more beat frequency as compared to the moving speeder. You can note it down. Here we can see a next generation weather radar. These radars can detect the wind speeds, the tornadoes, the thunderstorm, the precipitation, the rain. So these are used in the forecasting of the weather. These radars are also used at the major airports to detect the wind shear, because wind shear causes the crash of the airplane. Got it? Such radar scans are normally available on the internet. You can Google out and you can find the radar scan about your area's weather. Okay, I am sharing few links here. You may give it a try yourself. And the radar returns are indicated by the colors. Green color is kind of okay situation, nothing to worry about, but the red and magenta, they indicates the strong thunderstorm. In that conditions, the normal airplanes are advised to return to the nearest possible landing space. Got it? They need not fly until the weather is clear. So based on this information, I am bringing few questions. You note down all these things. A simple and easy question, so I request you to give it a try, then I'll be simplifying it. I hope you got the correct answer, which is 504 hertz. The solution is pretty simple. Suppose here is the radar system and here is the weather system which is approaching with the speed of 28 meter per second. The radar sends out the electromagnetic waves with the frequency F naught. These electromagnetic waves hits the weather system. The electrons in the weather system oscillate with the frequency what they receive here, what they observe here, and then these reflected wave move towards the radar. Suppose the radar receives the frequency F. Okay, the question is basically asking us the beat frequency. Since the weather system is approaching the radar, we can use the formula of F beat which we derived in the previous calculation, previous question. F beat was equal to 2 times F naught V relative by C. Got it? And what is the meaning of F beat here? F beat is actually F minus F naught. I hope you understand these things. Calculation is pretty simple. 2 times F naught. The F naught of this radar is given as 2.7 into 10 to power 9 hertz. 2.7 gigahertz. Putting the data here, 2.7 into 10 to power 9 V relative. Radar system is at rest. The weather system is approaching with a speed of 28. So put it here. C is 3 into 10 to power 8 meter per second, and your answer should come out in hertz. Got it? Simple mathematics will give you 504 hertz. Okay, note it down. Then I'll bring a similar question for you. Here is the last question of this video. So I'm simplifying it directly. Data is like as we did in the previous question. So here is the radar again, which is at rest. This time the weather system is moving away from the radar with a speed of 21 meter per second. The radar sends the electromagnetic waves with the frequency f0. f0 is 2.7 into 10 to power 9 hertz, 2.7 gigahertz given in the question. These waves get to the weather system and then reflected back, and then radar receives the frequency f. This time, which will be greater, f or f0? Radar system is detecting that the clouds are moving away, so the received frequency should be actually less. Okay, the source and the observer are actually getting separated. So I should write here that f is less than f0. You get this? Now calculation is pretty simple. Delta f is equal to minus 2 times f0 V relative by C. Minus 2 into f0 is 2.7 into 10 to power 9. V relative is this time 21. Radar is at rest and the cloud is moving away. So relative speed is 21. C is 3 into 10 to power 8. And here you get the unit hertz. When you do the computation, this will come out as minus 378 hertz, f minus f0. Or if you want to write the positive data, the f0 minus f will be equal to 378 hertz. The frequency sent by the radar will be more and the frequency received by the radar will be less, and that difference is this much. Got it? I hope you enjoyed all the informations. Stay awesome. See you again. Thank you.